what we saw a couple videos ago is that when using different methods of determining the outcome of an election on the same data, we can get a lot of different results. And I wanted to circle back to the class president example where when we did with plurality, Art won the election, but when we did board account, Ben won. And when we did pairwise comparisons, Debbie won, but when we did plurality with elimination, Debbie won. But when we did the method of pairwise comparisons, Kathy won, and she was actually a Condorcet candidate. And now that we're looking back at this, you can see, well, we chose these letters, not so randomly. And also, this data was designed to illustrate these sorts of problems. It's not exactly realistic data, but these issues can be present with real data as well. So it's I think it's a very good example to illustrate what can happen and some of the issues with voting methodology in general. But basically, notice that Art could have come from anywhere from first to last place, Kathy anywhere from first to third, Debbie anywhere from first to third, and Ben anywhere from first to last. So there's an extreme variation between the outcome, and this can lead us to believe or lead us to the conclusion, well, who should win? We have no idea. Anyone could win. And like, should we just pick from a hat? How do we actually determine it? And this is an obviously troubling feature of elections and one that humans kind of have been aware of for a little while. And this is exactly uh, where a good introduction into the last section of the book, which is 1.6, titled Fairness Criteria and Arrow's Impossibility Theorem. And this is a question that Dr. Kenneth Arrow sought to solve, and he did actually, well, in a way, he solved it in the 1940s. But he wanted to know essentially which of these which voting method is best, which ones are most fair, and if they aren't fair, can we devise a new method that is better than all of these methods that people use, so we can figure out the outcome in a more sensible way. And essentially, it's very important work because if we're trying to make an educated, informed decision as a society for electing, we want to have the best possible way of doing it. We have so many different ways that it's done traditionally, and we want to, basically want to compare each of those. But basically, he did a mathematical study of this, and he ran it through what he called his fairness criteria, and basically wanted to know, can any of these methods, are they all fair? And then what he wanted to know is, well, if they aren't fair, can we devise a new method which is fair and satisfies all of the traditional means of what it means to be fair? And basically, his conclusion is proof. We're not going to look at the mathematical paper and get into the nitty gritty of it, but his conclusion was it's actually impossible to satisfy all of his criteria, and essentially, it's impossible to have an unbiased, completely fair election system. Every single method of determining the outcome of an election has its flaws, and it's kind of what we have to do is be aware that flaws exist and kind of just be happy with it because it's impossible to actually do them all. So what I want to do next is actually look at, well, what are these fairness criteria and kind of look at where certain methods can satisfy them always and some aren't always fair. And this is kind of a way of how mathematically can we quantify what it means to be fair, and that's exactly what he did in his paper. So he had 4 criteria that he looked at and he proved that no method can actually satisfy all 4 of these at once. But basically, the first is called the majority criterion, and criterion is singular, whereas criteria is plural. So I'm going to try to not mess this up, but I almost always do because English is a language, and it's, again, that's why I teach math. But basically, the first fairness criteria was that a majority candidate should win an election, and this is another kind of historically common sense type of thing. Well, if we're going to elect someone to represent everyone, they should be preferred by at least half of the people, right? If only 40% of the people like this person, are they really that good of a choice? And obviously, if you have a lot of candidates, it's not always going to be possible to do this to satisfy the majority criterion as well. So you can kind of see where that comes into play. But like I've looked at a lot of my students' opinions on, because on the exam a question I always ask is to determine the outcome using a bunch of different methods, and then tell me what is your opinion, who do you think should win and why. But there's always a handful of people that believe that first place votes matter the most, that you should get whoever has the most first place votes, and if they have a majority should win the election. So next up is the Condorcet criterion, which says that a Condorcet candidate, this is misspelled, and I haven't managed to fix it yet, should win an election. Which, again, what that term meant is someone who is undefeated on a head-to-head basis in the head pairwise comparison. And when I was talking about the pairwise comparison method, I kind of mentioned, well, if you are better than everyone else on a head-to-head basis, that's a strong indication for a good candidate, right? If you are better than everyone else, if you're preferred, that's a good choice. Just like a majority candidate, if more than half the people like you, that's a good sign. As is a Condorcet candidate. And if someone is a Condorcet candidate, there's a strong argument for that they should be the one who's elected. The other two criteria are a little bit harder to explain, but I'll do my best. And if you look in the book, it doesn't quite say it this way, but I tried to paraphrase using kind of the more basic idea. But the monotonicity criterion says that a candidate should never be hurt by being ranked higher on a preference schedule. And basically this is translated. If you look in the book, it'll say it like if candidate X is ranked, and so something like that. But basically, imagine that we have a ballot, let's just say going back to the class presidency, and let's say that we've run through the determinations and we've come up with the answer that Kathy should win this election. But let's say that we switch, say these four voters, let's say four of those voters change their mind, and let's say that they actually have Kathy ranked higher than Debbie instead. So basically, Kathy would have won already, and let's say Kathy gets more votes or is placed higher. Let's say that after changing those votes, like say we swap C and D here, if Kathy now lost after being ranked higher, that would be an example of failing the monotonicity criterion. So basically, if a candidate is ranked higher and that somehow hurts their chances of winning, that's not fair, and that's the idea behind the monotonicity criterion. And monotonicity, that's a word in math that means like things are in order. Something that is monotone is like a sequence that's always getting bigger or smaller. But it's kind of like if we're keeping them in order, the ranking should stay in order. But if someone's moved higher, it shouldn't move their ranking lower, right? It should always have the higher ranking, higher results. But it should never hurt them for being moved up. And the last criterion is kind of similar. The independence of irrelevant alternatives criterion, or IIA for short, because that's a heck of a mouthful, which says that a candidate should never be hurt by another candidate's elimination from the election. Sorry, my head's in the way there. And basically, very similarly, let's say that between Art, Ben, Kathy, and Debbie, Kathy was going to win. But let's say that Art decides that they're gonna drop out from the election. They're gonna, and a lot of times people will drop out or will stop running for candidacy because of a lot of reasons. It could be money, it could be they don't think they're going to win, or whatever. They just changed their mind. That would obviously change things because if Art is now gone, now it's just an election between Ben, Kathy, and Debbie. And basically what could happen is that if Art is removed from contention, that could change the outcome, which wouldn't be fair either, right? Because the reason that this is an important criteria for fairness is that if Kathy wins, but let's say that after Art was dropped out, now Ben wins, it should not change for an irrelevant alternative candidate being removed, right? It should stay the same. And the reason why that could be unfair is that let's say Ben knows that if Art drops out, Ben's going to win. Basically, you could imagine, well, Ben might pay Art to drop out from the election so that Ben wins, and that's obviously could lead to a lot of unethical or bad things happening. And we don't want an irrelevant person's numbers to mess up the election in a way. So anyways, those are the four criteria that Dr. Arrow studied, and what he proved mathematically is that there is no mathematical method, not just the ones we talked about, but it's impossible to actually develop a system that could take all of these into account. And as you can probably see, these are all different ways of thinking about what's fair, and fairness in kind of in analyzing from the mathematical side, it's not really a mathematical thing. It's more of an idea. And there's a lot of different ideas for what people think is fair, and basically it's very hard to develop a system that is fair on all different levels based on the opinions of what that means. Um, and also, if you're really worried about this, on the test doesn't get into detail on all of these things, but really, I think this is kind of interesting to get into. Well, what's fair? What methods are good? And in the next video, I'll look at a couple examples so that we can kind of look at how, what would this look like um, in application? How do I determine what an example of a violation?